Welcome to the Deep Dive, where we plunge into the most important nuggets of knowledge and surprising facts, helping you get well-informed fast. Today, we're tackling something really quite astonishing in modern AI, in context learning, or ICL. We've all seen these huge models, GPT-3 with 175 billion parameters, PaL-M with 540 billion, and how they can just adapt, perform new tasks almost instantly from just a short prompt with a few examples.
It really does feel like magic sometimes.
It does, adapting on the fly, no full retraining needed. It's mind-boggling.
It genuinely is. And what's so interesting is this ability to learn very specific things from such minimal data, right? The model seems to almost implicitly train itself just on those few examples in the prompt.
Right.
And then it just applies that learning immediately. It's incredibly efficient, especially compared to updating the main weights, which for these models is just, hugely expensive and slow for every single new task.
Absolutely. It looks like magic. But, here's the thing. While we see this amazing adaptability, the deeper reasons, the sort of rigorous how and why it works so well, so reliably, that hasn't always been fully pinned down, mathematically speaking.
Yeah, the statistical foundations have been a bit murky.
And that's exactly where our deep dive comes in today.
Right. Our mission, really, is to unpack this fascinating new research paper entitled Generalization and Stability in Context Learning. And this paper, it goes further than just describing what ICL does.
Okay.
It aims to provide the theoretical bedrock, the actual evidence for how it pulls off these feats. It frames ICL through a really rigorous statistical lens, treating the transformer model itself as a kind of learning algorithm.
That's the key intellectual leap, isn't it? They're trying to understand how these models infer complex relationships just from prompt examples and then generalize that learning across different tasks. It's a very academic, very innovative way to look at something that often feels a bit like a black box.
Exactly. We're aiming to go beyond just observing it works to understanding the fundamental principles.
So let's start by really clarifying what in-context learning is in this specific context. Because, most people think AI training means updating those internal model weights over and over. But ICL is... it's the completely different paradigm, yeah. With ICL, the model's core weights, its base knowledge, aren't being touched.
Okay.
Instead, the transformer gets this prompt. It could be a sequence of inputs and outputs, maybe some question-answer pairs, or even like a whole little data set squished into text.
Right.
And the crucial part is it uses only the information in that prompt to make predictions on new stuff. It's immediate adaptation, real time. No back-end retraining involved.
It's like giving a super smart student one chapter and expecting them to ace the test on it right then and there.
That's a pretty good analogy, yeah. And what's really fascinating and relevant to this paper is how recent work has pushed ICL beyond just language.
Ah, yes. Gary et al. Laskin et al. Exactly. We're seeing models infer general functional relationships now. You can feed it, say, a whole training data set as a prompt, like numbers in a spreadsheet, and the model implicitly tries to solve that supervised learning problem on the fly.
Without any formal training steps.
Right. And that's where this idea of implicit optimization comes from. The model isn't doing gradient descent like in normal training, but somehow it's optimizing its understanding based purely on that prompt data.
Okay.
And using that understanding for new predictions.
Yeah.
It's this dynamic, on-the-spot learning that makes it so powerful for adapting quickly. It's not just memorizing, it's inferring structure.
Okay, let's unpack the first major innovation in this paper. And this is where it gets really rigorous, really exciting for understanding ICL's power. They provide finite sample generalization guarantees, which is a huge leap, right? Before this, it was mostly, well, it seems to work, or maybe some conceptual links. But this is more like a mathematical promise.
Exactly. It shifts us from intuition towards actual proof. And a core concept they borrow here is from something called algorithmic stability theory. Let's call it error stability. Okay. Error stability. What does that mean practically?
Well, imagine you slightly change just one example within the prompt you feed the model. Maybe you flip a label or slightly alter an input value.
Right.
A stable algorithm's overall prediction on new, unseen data shouldn't change dramatically because of that one tiny change. Its output should be robust to small perturbations in its training data, which in this case is the prompt.
Makes sense. You wouldn't want it to be completely thrown off by one tiny error.
Precisely. Stability is really fundamental for guaranteeing reliable performance.
And here's the real kicker, the part that connects the theory to practice. The paper proves that multi-layer transformers, the actual architecture behind models like GPT and PaL-M, they actually satisfied this stability condition.
Yes, under some pretty mild, reasonable assumptions, which is huge. It really is. It means this theoretical framework, these guarantees, aren't just abstract math. They directly apply to the complex models we use every day. It bridges that gap.
And they didn't just leave it at theory. They backed it up with experiments.
Ah, the empirical side.
Right. If you look at their results, figure 6, I believe, they show this stability empirically. They deliberately mess with a prompt like flipping one label and measure how much the model's test performance, its risk, changed.
And what did they find?
They found that as the number of examples in the prompt increased, the impact of that single flipped label on the test risk got smaller and smaller. It decreased consistently.
So the bigger the context provided in the prompt, the less sensitive the model was to a single error within it.
Exactly, which lines up perfectly with their theoretical stability assumption. It's strong practical evidence supporting the theory. A really nice convergence.
Okay, moving on. The next innovation is equally, maybe even more groundbreaking. It pushes ICL into totally new territory. See, traditionally, ICL research looked mostly at prompts with, what's the term? i.i.d. data.
Yes. Independent and identically distributed. Basically, each input-output pair in the prompt is assumed to be drawn independently from the same underlying distribution, like pulling random cards from a deck.
But the real world, well, it isn't always like that, is it? Especially with systems that change over time.
That's a crucial limitation of the old view. This paper makes a big leap by extending the theory to handle temporally dependent prompts. Think about data where each point influences the next, like trajectories from dynamical systems.
So not random snapshots, but a sequence, like predicting weather or a market or maybe how a physical system behaves over time.
Exactly, where the past state directly impacts the future state. This is a much more complex but also much more realistic scenario for many applications. It's a really significant new direction for ICL theory.
And tackling that complexity required some new theoretical tools, right? New stability ideas.
It did. They had to introduce, first, a concept of exponential stability for the dynamical systems themselves. Definition 5.1 in the paper. It basically controls how quickly different possible paths or trajectories of the system either converge or diverge over time. It assures the underlying system being learned is somewhat predictable.
Okay, so stability of the system being modeled.
Right. And then, building on that, they introduced algorithmic stability for dynamics. Assumption 5.3. This is a variation on a concept from control theory, input-to-state stability, adapted for learning algorithms.
How does that differ from the previous stability?
It measures how the transformer's output prediction changes, given perturbations not just in one point, but along an entire trajectory or sequence within the prompt. It's stability applied to time series data.
And crucially,
They prove lemma B.5. I think that multi-layer transformers also satisfy this more complex stability condition for dynamics, which is, frankly, a pretty heavy theoretical lift.
wow. So what does that mean for us for understanding ICL?
It means that their generalization bounds, those mathematical promises about performance, still hold, even in this much trickier dynamical system setting.
Okay.
Theorem 5.4 shows this. It implies ICL can be provably effective for tasks like predicting future states in complex time-dependent systems, which is huge. It really broadens the applicability of ICL to a whole new class of real-world problems.
Where the data isn't just a collection of independent facts.
Precisely. And again, they show visual evidence. Figure 11, for example, demonstrates ICL performing really well on these dynamical system tasks, holding its own against methods specifically designed for them. So it's not just theory, it works in practice on these harder problems too.
All right, let's shift gears to the third major innovation. This one is more about how we interpret what ICL is actually doing. The paper frames it as an implicit model selection procedure. That sounds profound.
It is a really interesting perspective. Instead of just seeing the transformer as a predictor, they view the transformer itself as kind of high-level learning algorithm. Given a prompt, which is a sequence of data, this algorithm, the transformer maps that sequence to a specific prediction function tailored for that prompt's data.
So the transformer isn't just predicting, it's choosing how to predict.
Exactly. That's the insight. ICL isn't just learning the task presented in the prompt. It's implicitly selecting the best underlying model type or hypothesis class for that specific task and data.
Like it's automatically deciding, okay, for this prompt, a linear model is best. Or for that one, I need something more like a neural net.
Precisely that.
Yeah.
Or maybe deciding between different types of regularized regression, like ridge regression. It's doing this automatic model selection on the fly without being explicitly told which model type to use.
And this connects to other work using ICL for AutoML, right? Like Holman et al.
Yes, exactly.
Yeah.
People have observed ICL behaving like an AutoML system. Just feed it a data set as a prompt, and it acts like a classifier or regressor.
Right.
What this paper contributes is the theoretical justification. It provides a potential explanation for how transformers manage to perform this sophisticated, automated model selection. It gives us the why behind the what.
How do they formalize that?
Well, we have hypothesis 6.1 and observation 6.2. Eventually, they argue and show evidence that ICL adaptively picks, the hypothesis class, the type of model that minimizes the prediction error, the excess risk, for the specific amount of data given in the prompt.
So it adapts its strategy based on the prompt size and content.
Yes. It's like it has an internal toolbox of different learning strategies, and it picks the best one for the job at hand, right then and there.
And the evidence for this, you mentioned numerical results earlier.
Absolutely. The numerical evaluations are quite striking. Look at figures 2A and 2B focusing on linear regression tasks. ICL, shown in red, doesn't just do okay. It consistently outperforms standard least squares. But more impressively, its performance curve perfectly matches the performance of the optimal ridge regression, or the optimal weighted regression solution for that specific dataset size and structure.
It's not just good, it's optimally good for that scenario.
Exactly. It's behaving as if it knows the best possible linear model to use for that data. This is really strong evidence that transformers can learn and apply these sophisticated task priors, acting like an automated statistician or model selection engine.
Wow.
And this adaptive selection ability is super important. As the paper notes, the kind of generalization bounds they derive, like decaying error with 1 year with Muhammed, or the prompt size, actually facilitate this. It means the model can achieve good performance without needing, say, an absurdly large number of different tasks during its initial meta-training phase just to learn all these different model types. It makes the whole process more efficient.
Okay, so ICL is incredibly powerful, stable, adaptable, even selects optimal models implicitly. But there's a nuance, right? Something maybe a bit surprising that came up when they looked at transfer learning.
Yes, exactly. A section of the paper, section 4, delves into how well ICL performs on completely new, unseen tasks, the transfer learning setting. And the findings here are quite thought-provoking, raising some interesting questions.
What did they find?
Well, one surprising result, highlighted in figure 7, is about model complexity. When they compared the transfer risk, how well the model did on new tasks using different sizes of GPT-2, tiny, small, standard, models with vastly different numbers of parameters.
Yeah.
The transfer performance curves looked remarkably similar.
So making the model bigger didn't really help it generalize better to totally new kinds of problems.
It seems not, at least in their experiments.
Yeah.
Which is counterintuitive, perhaps. You might expect bigger models to transfer better.
But then there was this other finding, the d-squared puzzle.
Right. Figure 8 touches on this. While the model size didn't seem critical for transfer, the number of source tasks needed during the initial meta-training phase seemed surprisingly large.
How large?
It seemed to scale roughly with d squared, where d is the input dimension of the tasks.
Okay, and why is that a puzzle?
Because more idealized theoretical learning algorithms often only require a number of tasks proportional to just d, not d squared, to achieve good transfer.
So ICL seems to need quadratically more task examples during its initial training to learn how to generalize broadly compared to what theory might suggest is optimal.
That seems to be the implication, yes.
So what does that all mean?
Well, it suggests that the way ICL models are currently meta-trained, while effective, might not be the most sample-efficient way possible in terms of the diversity of tasks needed.
It learns well, but maybe it needs too many different kinds of homework problems to get good at solving totally new ones.
That's a decent analogy. The paper speculates this might be due to an implicit bias introduced during the optimization or meta-training process. The transformer might end up favoring certain types of solutions or algorithms based on the specific mix of tasks it was trained on.
Ah, so its training diet might be subtly biasing its future problem-solving approach.
Potentially. It might not be learning the most universal or efficient mechanism for transferring knowledge. And this definitely points towards an important area for future research. Can we overcome this potential bias? Can we train ICL models to be more sample efficient in their meta-learning, requiring fewer tasks to achieve that broad generalization capability?
What a fascinating journey through this paper. We've covered a lot of ground, really peeling back the layers on in-context learning. Just to recap the big innovations quickly,
Yeah, first there's the establishment of a formal statistical framework. That's huge.
providing those finite sample generalization guarantees. Then the proof of transformer stability.
Right, showing these complex models are fundamentally stable under certain conditions. That builds trust.
And extending those guarantees beyond simple i.i.d. data to the much trickier world of dynamical systems.
Opening up a whole new range of applications involving time-dependent data.
And finally, that really profound interpretation of ICL as an implicit model selection procedure.
Yeah, revealing how transformers might be intelligently choosing the best strategy on the fly, like an internal auto-ML system.
This work really feels like an aha moment, doesn't it? It moves us beyond just watching ICL do amazing things to actually starting to explain it theoretically.
Absolutely. It gives us a much deeper, more robust, mathematically grounded understanding of how these incredibly complex models achieve what they do.
It's not just bigger equals better. It's about their inherent structure and how they learn to adapt and strategize.
And for you, the listener, this means we're getting a clearer, more theoretically sound picture of the magic. It's a step towards AI that's not only more capable, but also more understandable, more trustworthy.
And maybe as a final provocative thought to leave you with, this research highlights that even these powerful ICL models might not be fully sample optimal yet in how they learn to transfer knowledge. They might need that squared number of tasks during training. So the question becomes, what changes in architecture and training might unlock even greater efficiency? How can we help them learn to generalize powerfully from even fewer diverse examples, truly maximizing their potential across unseen challenges? Something to ponder until our next deep dive.